Okay, good morning. In the last class, we tried to motivate you on different types of problems which can be solved very nicely when they are converted to graph problems. Remember, we saw this problem on designing a traffic signal for this 5-point intersection, assuming that all traffic goes from left to is on the left hand side of the road, like what it is in India. And we found that although this looks like a very domitable task, designing a signal for this, we found that as soon as we abstracted information from this and transformed this to a graph problem where we made the nodes the directions and the edges corresponded to two nodes that are connected such that these two directions cannot happen simultaneously. We found that it was very easy to design a naive algorithm which was called the coloring problem, and all that we had to do was we start with a particular node, and let us say I start with AC, and then I say for this, if this is green, then it cannot be green for BA and BD. Whenever it's directly connected by two edges, then you cannot have, assuming left hand side traffic as in India. So we found that we could easily solve this problem by a very naive coloring algorithm and make sure that directions which intersect are not colored the same at the same time. And once all the nodes are exhausted in the graph with this coloring problem, every node has been colored, then we have a design of a traffic signal. So I guess this was a very nice motivating example to show why when you abstract to a graph problem, then solving becomes easy. Then we looked at representation of graphs, we defined what graphs were, and so on. Today what I am going to do is I am going to take one particular problem on two problems actually. One on the shortest paths problem, which is given a node and nodes and a set of vertices. Let us say these are the nodes that we have, a set of vertices, and given a set of edges, and the objective is this, this is a directed graph, let us say, and we are given weights on the edges to say how expensive it is to go via that particular edge, to take that particular path, and our objective is, let us say, let me put some weights on this. Let us say I have 8 here, 2 here, 15 here, and 3 here, and 2 here, and let us say 12 here. Okay. And our objective is starting with some vertex. Let us say this is the source vertex S. I want to go to all these destinations B, C, D, and E. My objective is to minimize the cost. What is the cost now? The cost of a particular path, for example, from A to C, I can go either via the direct path or I can go via B to C. And the total cost of the path here is 8 plus 2, 10, whereas the direct path costs you 15. So the idea is to find paths of this kind. For example, if there is a path from A to C via something else, which is cheaper than the direct path, then we should find those paths which are lower in cost. So the objective is of this algorithm is called a single source shortest path problem, a single node which is identified as source, and you need to find the paths from A to B, A to C, A to D, and A to D, A to E, such that the total cost of the path is minimized, that is the length of the particular path. So for example, if I am going from A to D, I can go A, B, C, D, or I can do A, C, D, and notice that 8 plus 2, 10 plus 3, 13, whereas this is 15 plus 3, 18. Therefore, this path is shorter from A to D than going from via C. Okay. Let us see how this algorithm works, and then most importantly, this algorithm assumes, it is important for this algorithm to work, that no edge has a negative label. That is very important to assume. And the algorithm uses, you already learned about the greedy paradigm and the dynamic programming paradigm. Here this algorithm uses what is called a greedy paradigm. As you already learned, greedy is what? We make local decisions which are optimal. We do not worry about the global optimum. But interestingly, what happens is in this algorithm, even though the decisions are made locally, these also scale for the global case. So even when you know all the nodes. So what we do is in this algorithm, we start off with a particular vertex A and say that I have what is called a source vertex list and a total vertex list. Then what I do is I initialize, let me say these vertices are numbered in the particular algorithm 1, 2, 3, 4, 5. So initially I say include the vertex A in the given list. In the algorithm, for example, I have said s equal to 1 because I am using an integer here to map the vertex name to this. So basically this is equal to 1 over here. And then what we do is we try to find the shortest paths to all the other nodes. So what we do is, for this we do a very simple algorithm. We maintain what is called a distance matrix, distance vector, sorry, and we maintain the distances to the other vertices. Let us say this is B, C, D and E. So first we, using the adjacency matrix that we have, we fill up this. For example, this information is given. We assume that the graph is of course completely known. The graph is static. Okay. So what we do is we have the direct edges. So I have from A to B the distance is 8, A to C the direct distance is 15, A to D I don't have a direct path, so I mark it as infinity, and in A to E there is a direct path, I mark it as 12. Okay. So initially I make a distance vector like this. Then what we do is, from the set of vertices we include in the set S the vertex that is closest to it. So if you look at 8, 15, 12, 8 is the closest. So what we do is to the vertex A in the directly connected edges. So we include in the vertex list the list B, and then what we do is we see whether there is a path to C that is via B which is short, and similarly I do this for the vertex D for the via B, and similarly we also look for vertex E via B if there is a shorter path. So what we do is, if you look at it here, so what is it that we have? We have a direct connection from A to C which is cost 15, and then 8 via B to C is 10. Therefore, this is shorter. So what we do is we update this path and call this 10 here, and there is no path still from B via B, there is no path to D, so we leave it as it is. There is no path via B to E, so we leave it as it is. So we have this updated matrix, and interestingly the vertex B is part of the source list. Next, what do? We again take the next vertex which is closest, for example, with from A using this distance matrix. Then we find that I include C here, and then from C now, so we remove it from the distance matrix. We know that the cost of the path from A to C is 10. Is there a shorter path from C to D such that the distance from A to D can be minimized? And that's obvious. A to D, our original distance was infinite. A to C, the distance is 8 plus 2, 10. 10 plus 3, 13. Therefore, we update this distance to 13. There is no path to E, so we leave it as it is. Okay. Next, what do? We choose the next vertex, which is again closest to this list, and then we get E over here. E is smaller in distance from A. So then we see if there is a shorter path from A to D. There is no other path here, and now we are done. So what do we have now? Finally, we include the vertex into the source list. Okay. So this is essentially what the algorithm is, and now what do we have? If you backtrack, you can get all the distances from the vertex A to each one of these vertices. Okay. That's what this algorithm is trying to do. If you notice, V in V minus S, it tries to keep updating this particular distance. So once we have, finally your matrix D will contain the list of vertices, the list of the distances from the source vertex 1, or as in this case A, to all the other vertices. The time complexity of this algorithm, notice that if you look at this over here, the cost of the to find the minimum over here, it's going to take you order n, and this is running n times. Therefore, the time complexity is about order n squared for this algorithm. We've already seen complexity analysis some time back, and this can be much better to order E log n if the number of edges in the graph is much less than n squared. With appropriate use of data structures and organization of graph, for example, if you used an adjacency list representation and then organize the edges in an appropriate data structure, you will find that the time complexity can be brought down to order E log n. Okay. So this is the single source shortest path problem of Dijkstra, By the way, I forgot to mention this algorithm is due to Dijkstra, one of the founding fathers of computer science. It's not pronounced as Dijkstra, it's pronounced as Dijkstra. Basically, he's Dutch, and that's why this Dykestra. Okay, the pronunciation is this. Okay, IJ is pronounced as I in Dutch. Okay, so this is the complexity of the algorithm. It's most important to note is that the edges cannot have negative weight. Why do I say that? Because it's possible that once a particular vertex has already been included into the graph, let us say, I had let me change this path over here, and suppose I had included this vertex into my list, and that's not a good idea. Keep it as it is, and there is a B, C, D here, and let's say I already included E into this graph here at some point, and at that time the problem is I cannot have negative edges, because if you look at this issue over here, as soon as the edge becomes negative, that negative edge gets included much later. Let us say this is 8 plus 2, 10, and this was, let's say this was minus 10 over here, and let us say I had another vertex here, C2, let's say F, which was 5 or something, and then I could go back to B like this, and so we have said that path length from A to B is 8 over here, and suppose this was minus 10, and I already included B in the source vertex list, therefore I'm not going to consider it again. But when you see here minus 10 plus 7 minus 3, right? So it's possible that from C there is a shorter path to the vertex B. Suppose this was already there at 15 here, and then let us say this was minus 10 plus 2, and I would have a shorter path to B via C, and this is precisely why we cannot have negative edges on the given graph. So 15 minus 10 is 5, 5 plus 2 7, therefore you have a shorter path via B, via C to B, C and F to B, whereas the original path that we have included is of length 8. So this is why this algorithm only works with positive edges. Why is Dijkstra's algorithm important? Especially today, in the day of networks, for example, we have a dynamically changing network, and for example, what could the costs be? The cost could be cost of, let us say, in the example that I have taken, it's possible that these cars, this is IIT Madras and you're going to Central Station, and which is the cheaper path is what you're looking at. This could be taking a taxi, whereas this could be taking the original graph, if you remember, is taking a bus for that matter. And whereas in networks today, it's becoming very important, because when you look at congestion that is there in the network, you can model the congestion as a weightage on the graph. It's a dynamically changing scenario, and you're constantly looking for better paths to transfer packets from one node to another on the network. Okay. So the next problem that I'm going to take up is what's called a minimum spanning tree algorithm. And if you notice here, the idea is, given a particular graph of this kind, the objective is to find a tree which connects all the nodes in the graph of minimum cost. Again, the cost could be congestion as in a network, or the cost of a link, for example. Here if I want to send something very fast, then if this is a fiber optic link, then the cost is very less, and things like that. This algorithm is again based on the greedy paradigm, and what do we do in this? Here the nodes are named 1, 2, 3, 4, 5 and 6. So what we do is, let's say, without loss of generality, I can take any node as the source vertex. Let's say I'm taking 1 as the node. Then what we do is, we incrementally keep on including, we basically partition the graph into 2 sets of nodes. One set of nodes which have already been included in the spanning tree, and other which have not been included into the spanning tree. So what do? I start with 1 and initially add the lowest cost edge into the tree. Okay. Then what happens? I have 1 and 3 in one part of the which correspond to the 1 corresponds to the tree edge, and 1 and 3 are the nodes which connect this tree edge, and they belong to one set. Then you have 2, 5, 6 and 4 which belong to the second set. Then what we do is, given this 1 and 3 are connected, I try to find from the original graphs which is the lowest cost edge which connects it to the rest of the graph. So here you find that all 3 are 5 over here, and this one is 6. From 1 to 2 the cost is 6, 3 to 2 the cost is 5, 3 to 4 the cost is 5, and therefore the 3 to 6 the cost is 4, and 3 to 5 the cost is 6. So what we do is, amongst all these edges which connect, 4 is the cheapest edge, so we chose the 4 edge. Okay, and now what happens? You have 1, 3 and 6 belonging to one set, and 2, 5 and 4 belonging to the other set. Now once again what you do is, you find out the lowest cost edge which will connect 1, 3 and 6 to 2, 5 and 4, which means this is the lowest. What is the lowest cost that we have here? Notice this 1, 3 and 6 have been connected, right? Now when we look at it here, you find the 6 is connected to the vertex 4 with a weight of 2, 6 is connected to 5 with a weight of 6, and 3 is connected to 2 with 5, 3 is connected to 4 with 5, and 1 is connected to 2 with 6. Therefore this is the lowest cost edge, so we take this lowest cost edge in, and finally we choose this last vertex to be connected. Once all the vertices are exhausted, your the algorithm is done. This algorithm is what is due to prim, and idea is, initially what do? We have 2 sets of vertices. U is a set of vertices, U and V is a vertex, T is an empty set initially, U is initialized to 1, and while V is, let us say, the original vertex set of the graph. Until all the vertices have been included in that U list, you exhaust every one of them. So what are we doing now? V is the original vertex set that's given. While U is not equal to V, let UV be the lowest cost edge such that U is in U and V is in V minus U. Then you make a tree with T union U comma V. Then you include V into the U list, just like we did over here. We started with 1, we included 3, and repeat this process until all the vertices are included in the U edge list, in U vertex list, which is the same as V now. The time complexity of Prim's algorithm is also order n squared, but if you use a priority queue with when E is much less than n squared and an appropriate data structure for representing the graph, you can get a better algorithm of order E log E, where E is the number of edges in the graph. Okay.